Okay. Good afternoon, everyone. Sarup, can you hear me?
Yes, sir.
Okay. You can see the slide also, right?
No, sir, not yet. Yes, sir.
I think 11th February is your periodical one. Sarup, you got the schedule, timetable?
Yes, sir, we got the schedule.
Okay. I think they have complicated it a bit this time. Immediately after the periodical, I'm supposed to conduct the Viva also. Okay, so it's going to be quite a lengthy affair.
Sir, it's on 10th February.
10th or 11th. Anyway, I'll check up. Must be 10th.
Okay, sir.
And that will be only up to module 1. Okay. Not whatever I'm taking now will not be covered in that. Fine?
Yes, sir.
And in between, we'll have a short quiz if possible. So, module 2 is all about navigation lanes. Okay. And I'll be covering only radar and TCAS in detail. A little bit on data bus, but more on radar and TCAS. That's what I intended. If the syllabus says that I'm supposed to cover everything, then it becomes too much. So radar is something which we saw in the previous course also. So it stands for radio detection and ranging. That's the acronym for. That's how we got this acronym radar. Like we discussed last time, it's all about sending one pulse. So it's just a pulse which goes and then gets reflected back. Then you find what is the time taken for this round trip travel, and then divide by 2 into speed of light will give you the distance. So primarily we are worried about the distance, and depending on which angle the antenna is pointing, but this is rotating around this axis. So if you look at the azimuth plane, it's going to be something like this. The antenna is going to look like this. And with respect to north, what is the angle? That is theta. So basically, we are going to get range information and theta information. And if it's a height finding radar, we can also get height. That was the primary radar. And secondary radars, in addition to all these things, it used to give even the identity of the aircraft and some emergency codes and all those things. That was the secondary radar. So 2 types of radar, primary and secondary radars. So both we'll see in detail. What this slide shows is the moment you start the pulse, you start a timer, you measure the time taken for the return pulse to come. So once you know the time, you can always find out the distance. And theta is directly coupled to the antenna axis, so you can derive that. The problem with radar is, though you can transmit huge amounts of power, even 1 gigawatts in some cases, like search radars, but what we are going to get back is going to be in few milliwatts. Okay. This comes primarily because one is we already saw. Suppose I'm transmitting 1 gigawatts, and at a distance d, what power will be received? We got some equations for it. Okay. In the previous module we have seen. Now, out of all this PR, not everything is going to come back. It's not a reflector. Okay, only a small portion is reflected back, The rest will be absorbed or scattered. So whatever is reflected is going to be a very, very small portion of the energy which is transmitted. And again, the problem is uh, in free space and in the environment, there's going to be a lot of noise. And in the presence of this noise, you'll have to discern this signal. So that's where the technology comes in. Colloquially, the reflected thing is called as an echo. And on the screen, it's called as a blip. So this will be the center yes, of the radar. And wherever the echo comes, it's called as a blip. These are all just some colloquial terms which have been used. So, as I said, it primary thing is range, bearing, elevation in case of height finding radar, and speed in case of few radars like continuous wave radars, which we'll discuss later. So this gives a three-dimensional reference. Like you have the north here, and whatever is the bearing that comes from the antenna axis, and if it is so, it's going to give the range. What you are going to give is get is the slant range. That is from aircraft to the radar, and it's not the uh, distance. Okay, actual distance, geographical distance. This you'll have to do some calculation and then try to get it. Otherwise, also it's okay. It's not going to create much of a problem for a search radar. But definitely in case of missile tracking radar, we'll have to take care of this uh, vertical angle also or the elevation angle also. So we'll discuss both in primary radar. We'll discuss both search as well as tracking radar. Tracking radar is nothing but missile control radars. A lot of frequencies are used again in radars, starting from VHF to KU band. But generally, you'll have L band radar as for surveillance. Few cases, S is also used nowadays. These are all search radars. Large volume they are going to search. And X band is what is used for missile guidance. So LS and X band. X is the tracking radar. And most of the radars fitted on aircrafts are all X band radars. I mean fighters. Okay. Whereas if you take AVAX, it will work on L band radar because it's a search radar. So what you will find in say LCA is going to be a X band radar. To the user or the air traffic controller, this is what he is going to see. A moving, it's called a raster. Okay, this whole thing keeps rotating like this. This line keeps rotating, and wherever he sees a blip, that will be highlighted. Whenever the radar sees a target, that will come as a blip. Sarup, any idea how we can retain this blip on the screen? Because the moment it crosses, the raster crosses, the blip should go off, right? And that's something we don't want. Are you getting the question?
Sir, it will stay till the next time the.
It should come, no? That is the ideal thing. So, but how does it stay? How can you make it stay? Anyone from the class? Just from your basic physics. Some material property which allows the light to uh, the lighted thing to continue till the time the next one is updated, or immediately the light doesn't vanish. Sanjay?
No idea, sir. Maybe the excitation of electrons.
Yeah, then but the light should not fade away, no, immediately. See, let us say the raster is at this point. It's rotating in this direction. So in time, at t is equal to 0, the radar has emitted a pulse and it gets a blip at some after some time. So the moment this blip comes, this gets illuminated. But now the raster itself is moving. After a fraction of a second, it has shifted its position. Okay, and again it will be doing the same thing, transmitting pulse. Every time it gets reset. Now, but for the user, it will be very annoying. No? Just a fraction of a second it comes, and then you lose the complete thing. And the air traffic controller is interested in all these aircrafts. There will be so many aircrafts. He wants a stationary picture of what's happening in this area. Of course, nowadays it's all digital. Okay? So you can have synthesized displays. But earlier days it was like this. Some material property which will allow this phenomenon. Just find out, okay? Now, generally, when you talk about radars, we talk about only ground-based radars. But uh, as we have covered earlier, the main problem is line of sight, and we'll have to lift the radar somehow up. Uh, One way is mount the radar antenna on this pylons or an aircraft so that it flies at a higher altitude and then you have a better coverage. Any other, as an aero engineer, can you give any other solution which is better than mounting it on an aircraft? Which probably will be a better option. So one was this, you have this antenna so that you can, even if there is a hillock here, you can see what's going on here. Okay, but as an, okay, I'll put it this way. As an aero engineer, would you like the pylon to be fitted like this over the fuselage?
No, sir.
Sorry? No, because it's going to create hell a lot of drag. Not only drag and just look at the stability also of it. It's going to be a nightmare because this pylon itself is uh, going to act like a lifting surface. Okay, we don't know, like if the aircraft is inclined like this. So this pylon is also like this and it's having an angle of attack. So you have another force coming up. So a lot of problems apart from the drag also. Any other solution you can give? Can you come out with some out of the box solution? But definitely it has to be lifted up. Sanjay, can you think of something? Some other alternative other than fitting it on an aircraft, but still lifting it up? Okay, a very simple solution, you can call it a very primitive thing, is you have a balloon, okay, and on the balloon at the bottom, you can always fit this radar. Uh, you heard about something called as aerostat, Saru, aerostat?
Sir, I heard. I guess I heard.
Yeah, and airship,
I'm sorry, sir.
airship, airship and aerostat. I just want to know what is the difference.
I don't know.
Yeah, anyone else in the class? Difference between an aerostat and an airship? Okay, as the name says, aerostat is something which is stationary, right? It doesn't have a power plant, whereas airships have power plants. And just for your information, all transoceanic flights up to 30s were all done by airships. Okay, they are massive things. In fact, they're all engineering marvels. So for that particular time, they were able to make such huge structures. And only problem with those airships was they were all filled with hydrogen. So they had a lot of accidents. Nowadays, airships are again coming back and they are using helium, okay, which is an inert gas, so that chance of fire is very less. So another version of this thing, it's more of an AEW type, and this is what I told you is an aerostat. Okay, so the radar is actually kept in this radar. What do you think, Sanjay, is the disadvantage of an aerostat? As a layman, what do you think is the disadvantage? Sanjay, can you hear me? Yeah. Or anyone from the class, what do you think is the disadvantage of this aerostat? Sandita? Sanjay, we can't hear you. You'll have to unmute your mic. Sarup, can you hear me?
Yes, sir.
Yeah. Can you just tell what can be the disadvantage as a layman of this aerostat?
So there's a fixed range.
Fixed location, right? Okay. So you can't move around. And this itself can be a good target for the enemy. So you can always fire at it. So that's why they're
Sir,
not used very widely. Yeah. Yes. Andita wanted to tell something.
the deflation with time.
Yeah, so periodically you'll have to, these are all permeable materials, so there has to be some leakage. So you'll have to keep filling up the gas quite often. Okay, now tell me, suppose some guy fires from bottom. Let's say the aerostat is here, and this is the ground, and some guy fires from the bottom. Some terrorist has sneaked into your territory and he is firing at it. Will the aerostat always come down or it can still come down slowly? It will come down slowly.
Sir, he shoots down the aerostat.
Yeah, he shoots from bottom. And let's say
Okay.
it's around 2000 feet.
Hmm.
This fellow is shooting from the ground level. Naturally, he's at the ground level. And what will happen to the aerostat? Will it come down immediately or it's going to take some time?
It is going to take some time.
Why?
Um, it's not like the material, say, if suppose it was a balloon, the
Mm-hmm.
material,
Mm-hmm.
then it would either go back because of the force or the damage, but the material here is different.
No, no, both are same. Okay, let's assume the balloon is also made with same material.
Okay.
What you are using in your birthday parties and all.
Right, sir. I don't know, sir. Something tells me that it'll come down slowly only, but I can't like pinpoint what makes me think that way.
Okay, suppose there is a leak. Naturally, it's going to be at the bottom. Okay, when the bullet pierces this, hydrogen being lighter, it's always going to be settled down at the top level, top portion. And whatever is coming out is just this small differential pressure. That's why even if they are hit, these aerostats, they come down very slowly. It's not like a UAV, if you just hit it, you lose the information. In that way, that advantage is there. Structurally, do you think there will be any problems in making this aerostat? And which do you think is the weakest area structurally?
Sir, won't it explode due to hydro?
No, it's helium, right? Nowadays it's helium. Had it been hydrogen, it will explode.
So attaching other parts to the aerostat is a big challenge.
Yeah, excellent, excellent. This is a big problem. All these stabilizing surface is a real nightmare. In fact, 2011 or so, few of our seniors tried to make one aerostat. So they were able to make this envelope all right, but attaching these surfaces became a big issue. Maybe sometime I could show you the pictures of that, of their project. Then this is the Indian AVAX those days. and it ended up as a disaster. Okay, it just crashed near Arakonam. Actually, what happened was this pylon detached itself, and then the aircraft went out of control while taking off. Again, the reason being the designers cleared the aircraft for a particular angle of attack, and what came out was the pilot exceeded the angle of attack. Naturally, the forces were much higher, which these pilots couldn't take care, and then it crashed. They did try this balloons also, but that also didn't work out. Finally, in India, we got this one from the Russian AES373, whereas the radar is an Israeli radar. This is what flies nowadays. In addition to the latest one being this Netra, which is actually an AEW, Airborne Early Warning, not Full Control Systems aircraft. What is the difference between these two aircrafts, apart from the size? What is the major difference you can see? Okay, this one is also mounted over the aircraft. You can see the radar mounted on the aircraft, and this here also you can see it. Apart from the color and all this stuff. Just look at the antenna. That itself is going to give you some clue. Okay, so it's nothing but this complete disk is moving. Okay, in this, on this axis, inside this radome is an antenna which moves 360 degrees. So the aircraft can have, suppose this is the aircraft, it can have 360-degree coverage. Now look at the Netra. The aircraft, let's say the aircraft is like this. Okay. And you find the radar fitted like this. So it's just one rectangular plate, you can say, or a small box. And now tell me how this fellow is going to achieve 360-degree coverage. With whatever we have learned about antennas.
So using side lobes, sir. Side lobes.
No, side lobes are not desirable. No, side lobes are not desirable. They create a lot of confusion. I hope the class is getting the point. Had it been a rotating disk, then definitely you can have 360-degree coverage. But now this fellow is just having one rectangular uh, shaped enclosure. And we learned something in antennas which will enable us to achieve this. And that rotating disk is structurally very weak, okay? And we don't want mechanically rotating stuff. So I already given you the hint. I want to avoid that mechanically rotating stuff. But still I want 360-degree coverage.
So some sort of reflectors.
Whatever it is, if it's a reflector, the reflector has to point in this direction. See, this coverage is actually the radar is pointing like this, right, on both sides. There is no problem. But how about this area? How do I get coverage in this area and this area? Direction rather, not area. We learned something in antennas which can do this. Okay, Sarup, we talked about phased array radars, right? So what is the advantage of phased array radar? Anyone from the class? Advantage of phased array radar?
So there are multiple antennas.
Multiple antennas will enable what? Good. Multiple antennas.
So they feed them with different paths.
Different paths, that is different phase. Then what happens?
So it can change the incoming. You can change the phase depending on the incoming power.
Yeah, that's right. And to the user, what's going to happen? What's the advantage? No? So I told you, this phased array radar, as UN is telling you, you can feed different, first of all, it has more than one element. And you feed it with different phase, you can actually steer the beam. Now this beam can be steered 180 degrees. You need not have any UN?
Sir?
Sarup, can you? Hello? Yeah, I think there's a problem. Sarup, can you hear me?
Yes, sir.
Yeah, yeah. Remember this phased array radar, what I was talking about?
Sir, I don't remember.
Okay. So when I told you that even without mechanical movement, we can steer the beam of the radar. Beam width we defined, right? 3 dB beam width. So now you can steer the radar without any mechanical movement. So you have two radars on either sides, and you can have 360-degree coverage. So that's how, without a mechanical movement of the antenna, this aircraft is able to achieve 360-degree coverage. Uh, there was one more aircraft called Nirmod. Okay, it was one of the earliest a British aircraft. What they did was they came out with a very different solution. They made a huge radome in the nose and one at the back. Okay, and then they had two antennas, one scanning the forward direction, the other scanning the rear direction. Obviously, the drag and all was too high, and that aircraft has been phased out now. Okay, but what we are going to see now is going to be all this phased array radars, and just out of curiosity, you people know what is going to be our next version of AWACS and how they are going to build it. It was recently in the news 2 weeks back. Again, someone has thought about a very out-of-box solution to make our own indigenous AWACS. They are making 8 of them or something like that. Some numbers 6 to 8. Some bureaucrat had a very good idea. He linked up few things and then said, "Why not we do it?" And then the government felt it's a very nice suggestion and they are implementing it. In fact, they are getting hitting 2 mangoes with one shot. So what they are going to do is, on one hand, Air India has become uneconomical, okay, to operate. So they want to get rid of those aircrafts. So this bureaucrat said, why buy an aircraft, use the Air India aircraft, and then modify it to with anyway we have the radar technology with us. All is required is just fitting those radars. So I think around 8 Airbuses, Air India Airbuses are being modified into AWACS now. So that's the latest on the AWACS technology. This is another phased array radar. You will find no mechanical movement. So just all these tiny things will have, each one will be an element. Okay. And then it will be, the beam can be steered. This was used during the Cold War to track incoming ballistic missiles. So the Americans used this sort of radars. Our own ballistic missile system also uses such phased array radars. More or less, they have, in fact, I think, deployed one system already in Delhi and Bombay. Then you'll have very small radars, battlefield surveillance radars, just very close to the border. A typical search radar will look like this only, a parabolic, not a fully perfect parabolic reflector, but something like this. But antennas are quite huge. This is what you see in all airports. Civil airports, when you land, you'll find this red and white painted radar dishes. So next time when you go to an airport, just have a look at it. These are all telemetry radars or deep space tracking radars. And yeah, this will be the primary radar. And over that, they'll have the secondary radar. Mostly this configuration will be there in civilian ATCs. And in aircrafts, naturally the volume for the antenna is very small. So you'll have a very small antenna. And as we have seen, lambda by 10 problem is there. So it will be in X band. So generally they will be having X band radar. And as I told you, it will be all nowadays it's going to be that AESA radars. This is one radar which I worked long time back. Okay, it's called P18, and you'll not believe it worked in VHF band. Now, after all these years, now I think the Aero India show has started. The Russians are again demonstrating a radar which can detect stealth aircraft, and they claim that uh, in such low frequencies, they are able to detect all the F-35s and all those things. We don't know how true it is, but these are all phased up now. We don't use it any longer. Okay. There's just a short introduction to radars today. Tomorrow we will start with the next class rather. We'll start with a little bit of theory on radars. Okay. Okay, Swarup, thanks. No, we'll meet in the next class.
Thank you, sir.